lower bounds from the Lyapunov exponent of 1D Schrodinger operator for the two estimates on the density of states.
It's a very long title. I'm sorry. What I want to tell you is based on joint discussions with Tom Spencer. What I would like to tell you in this short talk is about one-dimensional Schrodinger's operators on the line. These are self-adjoint operators on L2Z defined by h psi of n equal to 1 over lambda times psi n plus 1 plus psi n minus 1 plus Vn psi n, where V is called the potential and lambda is a parameter which is called a coupling constant, and in this talk it will be large. In the standard basis, these operators are represented by the following three diagonal matrix. It's just the matrix that have the potential on the main diagonal and 1 over lambda on two other diagonals. We will be interested in the operators which are called ergodic operators, which are constructed as follows. Suppose that we have a probability space omega p, and suppose that we have T from omega to omega an ergodic transformation. And let f be a real valued measurable function on omega. Then for any omega and omega, we can define a sequence v of n equal to v omega of n, which is the f of t n of omega, which is called the ergodic potential. The ergodic potentials is a wide class of potentials which include, for example, random IID and the almost periodic potentials. The corresponding operator h omega, which is equal 1 over lambda times 3 Laplacian, which is this part plus v omega, is called the ergodic operator. Many of the spectral properties of these operators, and in particular the spectrum itself and all of the spectral parts, are independent of omega for almost every omega. Now, the following are two main examples for this talk. The first example, I will take omega to be the unit circle and the measure to be the Lebesgue measure. Now I will take the transformation to be the shift of the circle by an irrational alpha. Then if we take v theta of n to be f of alpha n plus theta, when f is periodic of period 1, we obtain a potential which is called the almost periodic potential. In the second example, I will take omega to be two-dimensional torus, R2 over Z2, and the measure, once again, I will take it just to be the Lebesgue measure on the torus. The transformation that I will take, T of theta 1, theta 2, is the following transformation, theta 1 plus alpha, theta 1 plus theta 2, and this is called a skew shift. Now, if I will take f to be a function which depends only on the second variable, equal to f of theta 2, then we will obtain a potential v of n equal to f of half n square alpha plus a minus half n alpha plus n theta 1 plus theta 2. And these are two main examples for this talk. Now, one important example of the functions for this talk is the function which is called Morse function. Namely, it's f in C2. F is periodic of period 1. F strongly monotone decreasing on some interval 0a, increasing on interval a1. A minimum of f, it is f of a. maximum of f equal to f of 0 equal to f of 1. And we assume that the second derivative of f at 0 and respectively at 1 and at a is greater than or equal than some positive constant. Roughly, the function looks like that, which here is the f of a, here is the f of 1, and here is the f of 0. We would like to study the absolutely continuous spectrum of these operators, and this is exactly the part of the spectrum that corresponds to the absolutely continuous part of the spectral measure. And as I already mentioned, it is independent of omega for almost every omega. Let me mention a few cases in which it is our goal, saying, and I'm not saying what, our goal is to show that for large lambda, there is no absolutely continuous spectrum. And this is very natural and very intuitive, since if we take lambda, which is exactly equal to infinity, if you can say that, then we have an operator which is diagonal operator with only the potential on the diagonal, and therefore it has only pure point spectrum. So let me mention a few cases in which it is known, and I will draw some table. Example 1, example 2. And the cases of f and when it is analytic and when it is Morse. Example 1, in the case that f is analytic, was treated in 91 by Soritz and Spencer, in which they proved the absence of the absolutely continuous spectrum. In 2000, Bourgain and Goldstein find a different argument to prove the first example, which also covered the second example. For the case that f is Morse function, let me mention earlier works of Sinai from 87 and the work of Froelich, Spencer, and Whitwer from 90, in which, once again, they proved the absence of the absolutely continuous spectrum for the first example in case that f is Morse function. Actually, they prove much more. The result is much stronger, but I won't come into that now. And the example 2, the parallel result, let me mention the work of Chulaevsky-Sinai from 89.
When you say now absolutely continuous, do you know it's point or you don't?
Once again?
You know it's pure point or you only know there's now absolutely continuous?
I only know absolutely continuous. Actually, in these examples, it's pure point. In this example, it's no absolutely continuous. But for those examples, there's a pure point spectrum with exponentially decaying eigenfunctions. Now, the proofs of for the case that f is a Morse function uses a type of multi-scale analysis argument, which is rather involved and very, very hard to generalize. We are after soft methods which could be applicable in more general situations. For example, when Schrodinger operators appear as linearization of complicated nonlinear systems. The method is based on the idea of Tom Spencer, which appeared in his paper from '88, and we will discuss it shortly. But as for always, we have a price for that. So the price that we pay for the softer methods is that we won't be able to show the absence of the absolutely continuous spectrum, but only that it is a very small set. Namely, the measure of the absolutely continuous spectrum is smaller than or equal than e to the minus lambda k, where k equals 1, 2, and so on, hopefully for any k. The results in our work in progress, results that we have for right now, are the following. We have for k equal to 2, the first and the second example, in the case that f is a Morse function. Namely, what we have is that the measure of the absolutely continuous spectrum is smaller than or equal than e to the minus lambda square, And I will put a quotation mark here since it's not a very precise statement. And here I will write down that it is Morse. Now let me pass to the technical part of my talk. And first of all, I would like to define two objects, both of which appear in the title of my talk, which is the Lyapunov exponent and the density of states. Given an operator of this form, let us consider the associated eigenvalue equation h psi equal to e psi for real E. Now, for any n greater than or equal than 1, I will define n-step transfer matrix, which is 2 by 2 matrix that transfers the vector psi of 1, psi 0 into the vector psi n plus 1, psi n. The Lyapunov exponent, it can also be defined for n smaller than 1, but I will not get into that. The Lyapunov exponent then defined by gamma of E is equal to the limit when n tends to infinity of 1 over n ln of the norm of the n-step transfer matrix. It is known that this limit exists n independent of omega for almost every omega. The Lyapunov exponent measures the exponential growth of the solutions of that equation. And one can see, for example, that if the Lyapunov exponent is positive, then the solutions are either exponentially growing or exponentially decaying. Therefore, there is no AC spectrum. Actually, it is known that the absolutely continuous spectrum is supported on the set of E's for which the Lyapunov exponent vanishes. What we would like to show is the following. We would like to show that for large lambda, the Lyapunov exponent is of order ln lambda, except for a very small set of E's, namely exactly as I already said about this measure, except for a set of E's of the measure smaller than or equal than e to the minus lambda k for k equal 1, 2, so on, hopefully for any k. Now let me define the second object, the density of states. And it is just a probability measure. I will denote it by dk, and to emphasize the dependence on lambda, I will actually denote it by dk lambda. And it is independent of omega for almost every omega and supported on the spectrum. There's plenty of ways to define density of states, and one of the ways is to define it as an average of the spectral measure over the omega. Now, we have the following remarkable formula that gives a connection between the Lyapunov exponent and the density of states, which is called Pauli's formula, which says that the Lyapunov exponent is equal to ln of lambda plus the integral from minus infinity to infinity ln of e minus e prime dk lambda e prime. From that formula, one can see, for example, that if dk lambda of E has bounded density, then the second term is bounded, and therefore the Lyapunov exponent is greater than or equal than ln of lambda minus some constant. Namely, if k lambda is a Lipschitz function uniformly in lambda, then we have the desired result. Unfortunately, such a control over the density of states is rarely available. The problem of the regularity of density of states is considered a very difficult problem, and there are not too many positive results on this subject. Luckily, and this is exactly the idea of Tom Spencer, even crude regularity estimates on dk lambda implies that the Lyapunov exponent is of order ln lambda, except for a very small set of E's. Now let me formulate the statement precisely. I will denote by Z the set of all E's between B and A such that the Lyapunov exponent is smaller than or equal than 1 minus epsilon times ln lambda. And I will denote by G delta be the maximum between the delta and the supremum over all E between B plus eta, when eta is some positive number, and a minus eta of the integral e minus delta e plus delta dk lambda of e prime. Then the Lebesgue measure of z is smaller than or equal than 2e times b minus a divided by delta times exponent of minus epsilon ln lambda minus 6 eta ln of g delta e square divided by eta delta divided by 2g delta. Now, if you forget all the constants, then you see from this lemma that in order to have the desired result, all you need is to have the control over this integral, namely over the density of states on small intervals. And that's what we're doing using the perturbation theory. For a delta which is proportional to 1 over lambda, it's relatively easy. For a delta which is proportional to 1 over lambda square, it's more trickier and harder. And for a delta which is proportional to 1 over lambda to the k for k larger than 2, it's even more trickier and more harder, very hard. So we have several hopes. One of the hopes is to obtain these results for any k, for any fixed k. And the second hope is to apply these techniques to other families of operators for which all these advanced techniques are simply not available. Thank you very much.